This morning's talk will be presented by both myself, I'm Petra Selmer, and by Mark Needham. So I'm basically an engineer at Needham Technology, and I actually work on the Cypher compiler itself. And Mark, as probably needs no introduction, uses Cypher an awful lot. So between the two of us, hopefully we should be covering all areas. And essentially we're giving you some tips and tricks today about how to optimize your Cypher queries. Prior to that, we'll be giving you some definitions that may be useful for you to know as a background context to how Cypher actually works. And I'll also run you through the planner and actually how we execute Cypher. So the question may actually arise is, why on earth do we need to tune? I mean, surely, Cypher ought to be able to think of these things itself and, come up with the best way of executing queries. And actually, the truth is that no query planner is ever perfect. So essentially, Cypher will work 95% of the time. It will pick the best way of actually executing a query. But there is just that maybe 5 or 10% of situations, particularly for certain domains maybe, where actually you guys would know your domain far better than Cypher could, and therefore perhaps some manual intervention is required. So just a quick note about the cost planner. So probably this is quite familiar to all of you if you've been using Cypher for a while. It was prior to 2.2, we actually used a rule planner, which is just generally a not very intelligent heuristics-based way of actually coming up with an execution plan. And essentially from 2.2, we actually started being a bit more clever about this. And actually, we are now using statistics that we actually store in the actual database to actually try and come up with a much, much, much better query plan, resulting in far more efficient queries. And as of 3.0, all queries now use the cost planner by default, writes, reads, and everything. So this is essentially a very high-level overview of how Cypher queries actually execute. And I'll just run through this very, very quickly. There's actually a lot more detail in these two links at the bottom of the screen. So please feel free to have a look later on and come grab me or one of the other Cypher team, and we can certainly go through things in a lot more detail. But just to run things very quickly, essentially you write your query out. So query text coming in, the orange blob on your left. And this string is then actually tokenized and parsed. And from that, we create something called an abstract syntax tree, or an AST. And what we then do is basically we take this AST and we do some basic semantic checking. So are you doing something like trying to divide a string by another string, or something completely meaningless like that? If that is the case, then we immediately throw back an error to you saying, hey, return star divided by dog makes no sense. There's something obviously wrong there. However, we can actually trying to do other error checking as well, such as catching other basic errors. Provided we've got that far, we then actually normalize the AST. And this is basically a way of actually ensuring that for a multitude of operations, there's only one representation thereof. And that just makes it much easier for us to create the logical plan later on. So essentially what we'll do is move all labels and types, which you may put in your match clause, and actually instead move it to your where clause. So obviously it's equivalent if you write, where title equals the matrix or something, whether it's in your actual match statement or whether it's in your where predicate, it's absolutely the same. We'll just normalize it all to the same thing. We'll also do things like taking equals, equality predicates, and actually moving it all into an in. So where's something in, and then actually an array of values. And this, again, is just so we operate on a single representation for a particular operation. So from there, we've got the typed AST, and essentially from here, we then create an entity called a query graph. And this is essentially a very, very high-level abstract representation of the query, equivalent to the AST, but much more high level. And this actually makes it much easier for us to work on that rather than on the actual AST. From this query graph, we then actually create a multitude of logical plans. So this is actually now those blue bubbles over there. And essentially, this is now where we start hitting our statistics store. We actually try and see what labels are the most selective. By most selective, I mean will return the fewest results. So if you think about, you go to a restaurant. If you're selective about the restaurants you go to, you're going to have very few restaurants which you'll deem worthy of visiting. So essentially, we'll always try and get more selective starting points in our query. We'll also try and then get usage of indexes if they exist, as well as other things. And from this, we actually come up with the notion of estimating cardinality. Now, this is the amount of rows or records that are returned from each stage of the query. And again, we try and always optimize that the fewest number of results are returned. And essentially, this means we end up with a whole range of logical plans. And what we then have to do is execute an algorithm to try and find the best one. And prior to 2.2, we actually used something called the greedy search. But unfortunately, we were finding was actually finding not a bad plan, but perhaps not the best plan that there was out there. So actually from 2.3 onwards, we're actually considering a much wider space of logical plans. We're using something called iterative dynamic programming. And this has actually been proven now. We've run loads of benchmarking to actually find us much better plans in the same amount of time. So we actually are quite pleased with that. And essentially, so we choose our, fantastic winner logical plan, and then it gets converted into something called a physical plan. And this essentially is a tree closely corresponding to the logical plan, but now we actually replace it with physical implementations for each of the logical operators. And actually, we'll be seeing a few of them later on in this talk, and hopefully that will make a lot more sense. But anyway, this is just a rundown of basically what's going on in the background. So.
Okay, so we're going to be having a look at some queries, obviously, given that we're doing a bit of query tuning, and most of the time we're going to be introspecting them and having a look what's actually going on behind the scenes, and how is the stuff that Petra's just been describing actually being used, and is there anything that we can do to help it out? So there are two keywords that you can prefix your queries with to kind of see what's going on. So the first one's the explain. So that won't actually run the query. So that will give you the estimate of what it thinks the plan would be if it was to run it, but it won't actually run it. And then we've got profiles. That's your other keyword. And there we actually run the query, and alongside it, we're profiling it as well. And you get back the results of the query. And then on another tab in your Neo4j browser, you'd see that was what the plan was. And then you can see this the actual results as well. So they're useful for different things. This is the longest query plan we've seen so far. So this is from Stack Overflow. Now you might think this is it. That's page 2. And that's page 3. If you can beat that, that would be quite impressive, because this query was about 250 lines long. So yeah, don't try and beat that. But if you do, then Michael Hunger will attempt to reduce the size of the plan for you on Stack Overflow. And so this is what a query plan looks like. So if you run explain, or if you run the profile, that's what you'll see. You'll see something like that. And hopefully by the end of this, you'll understand what those operate. So each one of these is an operator. And so hopefully you'll have some understanding of at least the main ones that you're likely to come across. And you'll go, that one's a bad one. OK, I need to try and get rid of that one. Those ones are actually fine. I don't need to worry about those. And the goal when looking at these, and we'll look in a bit more detail so you'll see what does it mean, is we're trying to get the number of dB hits down. So obviously the first question you might ask, what is a dB hit? So dB hits is kind of an abstract way of looking at how much work's being done. And so if you run the query twice, you'll still get the same results. So it doesn't take into account any caching or anything like that. It's just a unit of work that the database is doing. And so it kind of gives you like a way of comparing queries against each other and going, well, that one's doing a bit more work than that one, but it doesn't really tell you, well, how fast is it going to be? Because it could be that putting it on a different machine actually makes it much quicker than running it. So on Petra's laptop, maybe it runs much quicker than my laptop, even though we see the same number of dB hits. So it's just an abstract sort of thing. You can compare plans against each other. And so we're going to have a look at some operators. So these are the main ones. So Petra mentioned there was a bit of preamble so that you can understand what we're going to do. So these are the main operators that we're going to be using for this session. So we've got the all node scan. So if you see the all node scan, that's a really expensive one. That's the equivalent of select star from star in your relational database, which you can't even do. So that's obviously not a great one to have. Then we've got the label scan. So that's a bit better. That's like the select star from table. And then the ones where we're much happier are where we're seeing index in the name. So it's like, cool, we've used an index to go and find something. And there's a couple of those. So we've got the index seek, and that kind of goes and narrows in on a particular node, or it could be an index scan where it's actually getting a range. So we get several of them. And you can read up about the execution plans in the documentation as well. So the data set that we're going to use to demonstrate this is one called Cine Easts, and this is it's really similar to I'm sure, how many people have downloaded Neo4j 3.0? Good, we're paying attention in the keynote. So if you were to download Neo4j 3.0, start it up, type :play movies, you get a movies graph, which is a bit of a kind of a subset of the one here. So hopefully if you go and play with this afterwards, you can go, oh yeah, I remember seeing those domain terms, and you'll be able to go and apply some of the knowledge and and see whether or not you can optimize queries on that data set. Right, so let's start. Let's start with a really simple query. So we're going to start simple, and we'll build it up. We'll build it up over the next 20 minutes or so. So for how many people is this the first Cypher query that you've seen? It can't be. You've seen one in Emil's talk. Okay, we'll ask it a bit more nicely. How many people have seen Cypher before today? Okay, so mostly. All right. Okay, so we don't need to spend too long explaining it. So basically, match is like we're doing a read query, and we're saying, hey, database, I'm going to give you a pattern. So in graphs we talk about patterns, and we're saying there's going to be a node. So that's kind of imagine that's like your circle. I'm saying there's going to be a node, and I want it to have a property titled the matrix. Okay, so when you pick it up, you might get your Nif4j, and you're like, cool. I'm really familiar with relational databases. I'm just going to do a really quick query. I'm going to find the matrix in this movies graph that Mark's told me to play. And so you run it, and you're like, I've got to use some of that profiling knowledge. Oh, no. So we've got the all node scan straight away. So there's 65,000. That's basically telling you there's 65,000 nodes in our database. And we've scanned all of them going to look for the matrix, which is kind of a bit more work than we might have imagined was going to happen. So tip number one, so this is going to be the structure. We'll show something, we'll have a tip, then we'll try it, and then we'll compare it. So that's your format to follow along with. So the first thing we're going to do is we know that in this data set we've put the movie label on some nodes. And in this case, the matrix happens to have a movie label on it. And so we can use that. So instead of just having just movie on its own, we're going to say, well, I know that it's going to be a movie, so let's use that in the query. And if we use that and we profile that query, then instead of the all node scan, which is quite expensive, we get a node by label scan instead. So you can kind of see it changes up here. And the number of hits has gone down to 12,000. And if we just put them side by side so that you can see the difference, on this side we had a 65,000 and a 65,000. So we kind of had 130,000 bits of work to do. We've got that down to 24,000. So you would roughly see probably a 5 times improvement in the amount of time it took to do the query as well. But we can do better, and Petra will show us how.
Indeed. So the next item is indexes and constraints. So again, what we can actually do is create indexes for non-unique values, such as exemplified by the first 2 statements. So we create an index on all nodes labeled with the label movie, and we actually want to index the title property therein. And the second one is actually where we want to have a uniqueness constraint. So this is basically for all nodes labeled with genre. We want to assert that any name property that is assigned to such a node is unique throughout the database. So this is just a bit of a kind of a sort of taking us back to the relational world is a slight, well, more than a slight difference actually. So in the relational world, we tended to typically use indexes for actually doing the joins. So essentially, we index the join table and other things. Whereas actually for the graph, we very much are only using indexes to find the starting points for a query. So anything that can actually narrow the amount of starting points is essentially what we are trying to aim for. Just watch out, by the way. Try not to index absolutely everything. So I think once you've got familiar with your domain and you've got your model and everything, try and only index those properties that you know you'll be querying very, very frequently. Because if you start indexing everything, it will almost be like having no indexes whatsoever. So just watch out there. Right, so going back to assuming that we actually have an index as we created over here, 2 slides back. So create index on movie title. Going through to this query over here, we can actually see that because there's an index on the title property for all movie labeled nodes, we actually have a very, very, very nice plan which uses the node index seek. Only 1 row, and that's actually exactly the row we want. So that's going to be super, super quick. So that's actually a nice thing to see. And this is just actually, again, contrasting. So the one on the right is what we absolutely want. The one on the left is pretty much, yes, not all that great. So node by label scan, you can see, is far more expensive. So yeah, there's orders of magnitude difference there. Right, back to Mark.
Okay, so let's make the query a bit more interesting. So this time, instead of just finding the actor, so we're going to find Tom Hanks. Then we're going to follow an acts in relationship. So that's going to take us to a movie here. Then we're going to follow the acts in relationship again on the other side. And we're going to follow it to another person. So we're basically finding how many movies are there that Tom Hanks and Meg Ryan have both been in. So the count star sort of gets rid of any of the, so if we didn't do the count star, we'd get like effectively all the paths where they were together. By doing the count star, we just get the sum of how many rows there were. So if we run that one, so this one's a bit smaller, but the comparison is what is interesting. So we're kind of doing a bit of work. We do a node index seek, so that Petra just showed us, and you probably can't see this at the back. This is a B, so it's kind of started from Meg Ryan, and then it's expanded that. It's then followed and done that, and then it's got up to, and then it's gone and filtered all the people to find Tom Hanks. And so you might look at that and go, okay, that's not bad. But we can actually do a bit better. So we might happen to know that if the query was to use 2 starting points instead of 1, so it's kind of started at Meg Ryan and then gone across, we might know, oh, well, actually, I think you can actually do better if we start from both places and then find out where they join together. And so what we might say is, well, actually, I'm going to give you a hint. So there's a using syntax where you can say, OK, planner, I think I know better than you. I think what you should do is use an index on A, person name, i.e. that, and you should also use an index on B person name. So that. So we're saying use an index for this and use an index for this, and then do the rest of your work. Hello.
Hi. So why wouldn't it do that already? What would the execution plan do?
Sometimes it does. Sometimes it would pick that up for you automatically. I guess there's some occasions. I mean, there's some occasions where it just doesn't get the perfect plan, and you happen to know better than it does.
Certainly, you shouldn't start with this from the outset. So you only actually put this in if you're noticing time and again that for that query, it should be using those indexes. You know, how obvious is that sort of thing? But it's not. Then you'd actually start using these. But certainly, don't do it from the outset. It ought to hopefully find it. But depending on what data you actually have and what statistics there are and what other indexes you have, things may not work out that way.
Okay, so we put that in, and then we go back to our browser. We put the profile in. Then we see a slightly different plan. So you can see now that it's kind of started from 2 different sides, as you guess it would. You kind of imagine it would. So we've got a node index seek starting from B, so from Meg Ryan, and we've got another one starting from A. That's Tom Hanks. So we kind of start from both of those. Then we expand this out, and then you can see here we're doing a hash join on the 2. So we kind of take the rows and we're sort of joining them together. And if we compare them, so on that zone, so you can just see what's a completely different way of processing the query. If we compare them together, you can see that the dB hits now goes down again. So on this side, we've had a bit of work here. So there was kind of 500. So the red sort of, the height of the redness of this dB hits indicates kind of how much work is happening. And so here we can see there's 354, 500. And on this side, we've got it down into the 50. So we're doing dB hits-wise 10 times less work to get the same result. So if we go on to the next one, so now instead of counting the movies, we actually want to get the distinct ones, and there might be multiple movies that they've worked in together, and that could absolutely be a valid query to do. So it could be that you actually go, I want to find the movies they've worked together. Here we're saying I want to get just the unique ones where they've worked together, and so we might write our query like this, and we use a distinct, so the distinct stops. Sorry, hang on, I've badly explained this. This query is slightly different, so we're saying Tom Hanks acts in a movie, someone else acted in the movie, they acted in another movie, so it's kind of going sort of 2 levels deep, and we're trying to find those other movies. So kind of like making a movie recommendation type query, I suppose. And we don't want to, and it's possible that M2 could show up lots of times as a result of there being different ways that you can get to it. And it could be that that instead of writing this distinct query, we say, well, actually, I'm just going to show M2 title, comma, count star, and see how many times did each one show up, and order by that. But for this one, we're saying, let's just see what distinct ones there are. So this is the new keyword for us. And so we might write it like this to start with, and this is the plan that we'd get, something like this. And so you can see there's quite a lot of work here, and then there's quite a lot of work again once we start doing the distinct. And so the way that we can optimize this is by reducing the amount of work in progress that we've got. So you don't see it so much on smaller queries. You start to see this more as you start to combine lots of different types of, I suppose, lots of types of traversals on a data set into one query. But here, this coactor from the previous query is actually showing up lots of times, because there could have been lots of movies that you've worked with the coactor in. And so but there's no point going and looking for the other movies they've acted in, because it's always going to come up with the same set, and then you're going to have to reduce it. So what we can actually do in this case is move the distinct up. and we can just do it up here instead. So we kind of go distinct on the coactor, and then we just do the next bit of our query just after that. And if we do that, the query plan becomes a little bit simpler. So we kind of reduce the amount of expanding that we're having to do, and we reduce the work that we're doing in the distinct. This one's a much more subtle improvement. So we've kind of taken it down from I think it's about 10,000 to about 7,000. You'd really see the benefit of doing this if you were doing like a Twitter or a Facebook type query where you've got a friends or a followers graph and you're going through someone who's very popular and they show up lots of times in the query. In a movies graph, there's only so many movies that somebody can be in a year, and so therefore, yeah, it tends to be a more slight difference.
It's basically coming back to the hints. So as emphasized earlier, please, please, please do not put these in from the outset. So this is only for those few percentage of queries that simply are just not coming up with very, very good plans. So just to really emphasize that. So essentially here, we're forcing the use of a specific index. So here we actually are saying, as was shown earlier, use the index on that on a person-labeled node with a name property. Another trick, and again, this falls into the same one. So the using keyword, as I say, treat with caution. But another thing you can actually do is you may actually have, say, the movie label has many, 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 many nodes, but maybe only a few of those have a comedy label, which actually means that a comedy label scan would actually return very few rows. However, because we normally prefer an index seek or an index scan to a label scan, we'll generally always try and use the index version. But actually, in some queries, that may not actually be the best plan to come up with, in which case we may actually want to force a label scan. And this is when you actually use this keyword. So it's very, very specific. And as I say, only do it once you have an idea of what your data is like, how many nodes of one type of label you may have. But this actually has been proven to work in some cases. So as I say, if you find that this is what your data looks like, try using this. And we've got a few more tips for you as well. So probably of those of you who've used Cypher before, how many of you regularly use parameters rather than actual values? Okay, so some. Yes, so what I can actually say, absolutely, please, 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 if you can, using parameters is the way to go. So essentially the bottom option over there. This basically means that every time you execute your query, by using parameters, we actually can notice that it's exactly the same query as before, okay, with different values, but that doesn't matter. The actual shape of the query is exactly the same, which means we can actually reuse the query plan we came up with previously. So we cut out that whole step of actually trying to find the cheapest logical plan and all that jazz that went on beforehand. So please try and use this. And actually how this actually works is we cache our query plans, and these get evicted basically either when the stats have changed, the underlying statistics have changed a lot, or after about 1,000 transactions. And also there's a parameter you can set to actually state after how long you can actually evict query plans. But anyway, this really is by far the best way to go. So in production code, please use parameters. And yes, whoops. So I've fallen into this trap a few more times than I care to mention, very embarrassingly. So Cartesian products. So that top query is, not only is it badly, badly wrong, but it's going to actually work like a dog, basically, in production. Really, really a super bad idea. So instead do, so if you're wanting to actually count nodes in the way indicated by the second query, that's one you should use.
Okay, and so quickly to wrap up, so we sort of realized sort of over time that people often or sometimes wrote queries and didn't realize that something crazy was going to happen from writing it. And so in the browser now, when you start writing queries, we'll actually start trying to give you some tips of what might not be a great query to write. So for example, so the Cartesian product that Petra just showed, if you write that, so by the way, the equivalent of what this is doing is it's saying find every node and combine it with every node in the database. So if you have 10 nodes, it's 10 times 10. If you have 100 nodes, 100 times 100, you can kind of see how it works. And so you'll get a little warning sign in here. Actually, as you type it, you'll see it. It'll pop up. You'll get a little yellow sign up here. And you can click it and it'll say, hey, Cartesian product, you shouldn't do that. You also get these tips for other things, like if you try and use a label that doesn't exist, or a relationship type that doesn't exist, or a property type that doesn't exist, they'll all pop up in there. And then once you've run the query, you'll often end up then seeing, oh no, it's running for ages. So you just need to kill it, put an explain on there, and you'll get the warning tab on your result, and you can have a look and see what actually does it think's happened. So the warnings are quite helpful. So kind of just to wrap up, so we've been talking about the cardinality. So you want to try and reduce the number of rows that you've got flowing through, both in terms of intermediate state and in general. And then this is another one is only return what you actually need. For example, on your web application. So a very common way of writing a query would be to write it like this. So I just go find me the actor, get effectively every single column that I've got for them. But then I actually only show 3 of them, and let's say there's 10 properties. So now I've basically returned or gone and serialized 7 unnecessary properties across the wire into my application. I'm not even going to use them anyway. So this is often another tip that you'll see, although there's no real way of seeing that. You won't see that in your DB hits. You'll just see, oh, it seems to take a long time for me to get all this data. And so that's something that is often useful to keep in mind. And then, in case you fell asleep and just woke up now, this is your TLDR. I should have told you this was coming. So to summarize, so have a look at your query plans. If it's not running how you expect it to run, put an explain or a profile on there. Use labels where you can. Put indexes on your starting points, but don't index every single thing, otherwise you'll make Petra mad. Don't want to make Petra mad. And try and reduce your work in progress. This is the one this one is sometimes not obvious to see. What is work in progress? So you might have to go and cut out some of your queries. So you might have a bit of a complicated query, and you're like, oh, it's not running as fast as I can. Try and delete parts of it and count the intermediate bits and try and work out where is it expanding. That's typically the only real way that you can figure out what's going on. And yeah, remember the hints. And then to quickly wrap up, if all these hints didn't work, we have a human planner who's over there in the lab coat. We've kind of got like a sort of internal joke that we should have. Oh, I want to set my query planner to Michael, and it should just send him an email with your query and go, hey, fix it. We haven't got that yet, but Stack Overflow is our next best option. So yeah, I think we've reached the end of our time. Thank you for coming. Thank you.